Hi folks. So I want to make hopefully a short video about the math I used to design the battery for my e-bike. First place you start is your power requirements, and I'm not really sure what the power requirements are because I'm using a motor that is not designed to do what I'm asking it to do. So I'm kind of guessing on the power requirements. So I played around with a whole bunch of numbers, and for example, down here, I calculated how many watts I was putting into the motor in my last video, which I had 24 volts and 12 amps, and it turns out I was putting in 288 watts into the motor. And if you watch that one, you see that I couldn't slow the motor down, even wearing even squeezing the output shaft with a gloved hand. And that was with just 288 watts. And I'm planning on putting in anywhere from 500 to 1500. I'm not sure yet. So that's kind of where I'm starting. I don't have any definitive figures of, this is what we really should use. I'm just kind of guessing as I go. But it all seems to be working okay. So I'm going to figure right around 30 volts and 50 amps maximum, which is going to give me 1480 watts if I put it all the way to the maximum, and that's at nominal voltage, which would be, in this case, nominal voltage would be about 30 volts. And let's pretend that we want the battery to run for an hour at 1480 volts. So we need a battery with at least a 50 amp hour capacity and 1480 watt hours of energy. That is so we got volts, amps, watts, hours, amp hours, watt hours. Those are the key factors that we want to take into consideration when we design a battery. So next we need to find out a little more information about the individual cells that we're going to use. I happen to have 132 identical cells, Samsung ICR 18650 22F, and the information I have on them comes from the forum database. And so that made it really easy to just copy those numbers right in here, with the exception of the capacity, which I had to get from testing each cell. But they all averaged out to about 2.1 amp hours each, which gives us 7.77 watt hours for each cell, and each cell is capable of delivering 4.4 amps continuously, according to the database, the data sheet. So yeah, so we have volts at full charge, nominal, full discharge, the capacity, the watt hours, the maximum amps, and that is the pertinent information for the cells we're going to use. So next we're going to put the power requirements and the cells together to figure out what configuration we want the battery to be in. How many in series, how many in parallel. So that's what this little table right here is for. You get how many in series by knowing how many volts you want total, divided by 3.7 volts nominal, and you get 8 in series, 8 cells in series, and we round that to the nearest whole number, which is 8. So that's pretty easy. And then we calculate how many cells do we need to produce the watt hours that we want the battery to have. Well, I wanted the battery to have 1,480 watt hours total, so that it could run for an hour. But that would require about 192 cells in total. And I again, I have 132. I don't quite have enough cells to do that. So I came up with, I did some calculations over here in this area here to get me some numbers that would be, whole numbers. So with an 8S configuration, I can have a maximum of 16.5 cells in parallel with 132 cells. And of course you can't have a half a cell, right? So you have to round, well in my case I have to round down because I can't round up, then I'd be over 132 and I don't have that many. So round down to 16 and that leaves me with 128 cells that I can actually use. Here I'm going to put 128 cells that are going to be in the battery total. And then of course we work out how many do we need in parallel for the watt hours. And if we're going to have 128 total, well that's easy. We just divide 128 by 8 and we get 16. And then of course, if that didn't round, or if that wasn't a whole number, we would round it to 16. Then we need to know, and a lot of people forget this one, we need to know how many cells in parallel to use in order to cover all the amps we're going to use, especially when you're working with laptop cells, which are often rated only at like half an amp or 300 milliamps or 1 amp, and you can't draw a huge amount out of those cells without heating them up, because they were never designed to do that. So you have to take into account how many amps are you going to draw through each cell. So to calculate that, we have the total number of amps, okay, for the entire battery divided by how many amps per cell, okay, and what we get is we need at least 11.36 cells in parallel in order to cover the amps needed. And again, you can't have 0.36 of a cell, so we round up to 12. Now what we do is we have two different numbers for parallel. We need 16 in parallel for the watt hours, we need 12 in parallel for the amps. So we're going to take the larger of the two numbers, and that's going to be our parallel number. In this case 16. So we're left with 8S16P as our final battery configuration. Now we go on to the last table in this area, and that's the actual battery characteristics that we're going to have. So way up here we have what our ideal would be, or what our system wants, and down here we have what we're actually going to get. And we can compare the two and see if there's any drastic faults going on. So we know we want an 8S16P battery configuration. We're going to have 33.6 volts when it's fully charged, and 29.6 volts when it's running nominally, and then 24 volts when it's discharged. And if we compare that to the system voltage, I did that on purpose. That's spot on there. What next? So we're going to have a usable capacity of 33.6 amp hours and a total energy of 995 watt hours. And if we run the battery full out, we can produce 2083 watts. And that would be at 70.4 amps, which is 4.4 amps per cell times 16 in parallel. We can pull 70.4 amps out of that battery. We're not going to, but that's the maximum. And so that is plenty. If we compare it up here, we only need 50 amps, and we only need 1,480 watts versus the 2,000 watts. So far the battery is looking pretty good, except for this 995 watt hour. That is, or I have over here rounded to 1 kilowatt hour, but yeah, it's 995 watt hours. That is below the 1,480 watt hours I was hoping for. So that's where limiting the cells has limited what I'm going to be able to do with that battery. But you know what? I think that's going to be okay, because we're talking about running the bike for an hour at full capacity, right? Which I don't see that we're ever actually going to do that. That would be like going up the hill all the time for an entire hour. And there's just no hills around my house where it takes an hour to get up the hill on a bike. If you're actually, moving at a decent speed. So I think, so the actual usable time of the bike is going to be somewhere more than what it would be if we were using the battery full out, which in this case is 0.67 of an hour. I don't really know how many minutes that is, 40 maybe, but that's if you have basically, full throttle all the time, which I'm not going to do. So now that we have the configuration and the stats here, we can go ahead and put it into a kind of a grid. This is kind of the final step that I do before actually building the battery, is I put it into a grid as if I'm going to make it just a basic rectangle. So every green cell and yellow cell that you see here represents an 18650 cell, and each number represents the milliamp hours that cell got tested at. Now, I haven't run this through the cell packer yet, so the numbers aren't really balanced as good as they could be. But what you can see is I've got 8 columns, which represent 8 series, and then I got 16 rows. Each row represents one cell in parallel in each series, right? And so we add up the individual amp hours of the 16 cells that are in the series there, that are connected in parallel, and we get 3,000 something. And we do that for every column, right? And so we get the total milliamp hours of each column, each series, and then to get the total capacity of the entire battery, we add those up and divide them by 8, right, to get the average milliamp hour, which is 3,300 something, 33.6 amp hours, roughly, which over here, somewhere, right here, 33.6 amp hours is exactly what we calculated, so, we're doing good so far. And then another thing is we're going to be running a maximum of 50 amps through this whole battery, right? So that means that each series is going to experience 50 amps. And every cell in that series is going to experience a fraction of that 50 amps. In this case, because there are 16 cells in parallel, every cell is going to experience 1/16 of 50 amps, which works out to 3.13 amps. And that's maximum, 3.13 amps per cell, and that is plenty below the 4.4 amp maximum from the datasheet. So that gives us a really good idea of how we're going to build this battery. Now, of course, I'm not going to build this in a perfect rectangular shape. I'm going to build it so that it fits inside the bike. But exactly how I'm going to build it and what shape and all that, I'm going to leave for another video, because this one's already getting pretty long. There's tons of information on how to do this on the DIY Powerwall forum, which actually is another name now. I'll put it down in the description. So anyway, I hope you find this helpful, even if you don't find it entertaining. And as always, thank you for watching.